Okay, CNN provided a television channel targeted to individuals waiting in supermarket checkout lines. The channel showed news, short features, and advertisements. The length of the program was based on the assumption that the population mean time a shopper stands in a supermarket line is 8 minutes. To test this assumption, a sample of actual mean waiting times from 120 shoppers showed a sample mean waiting time of 8.5 minutes. Assume the population standard deviation is 3.2 minutes. Okay, notice that the wants us to test to see if the actual mean waiting time differs from 8 minutes. In that case, to be different would be to be greater than or to be less than. So this is going to be a two-tailed test. We'll assume that the average time is 8, and the alternative then is that it's not. Step 2 is a sampling distribution. Again, this is a two-tailed test. We'll assume the average is 8, but we'll have a decision line on both ends in this case. Our alpha is 0.05, so in a two-tailed test you split alpha over 2. In this case is 0.025. And if I would use a table to get the z-scores for that, at the lower end it would be a negative 1.96 and a 1.96 on the upper end. Standard error would be the standard deviation, which was given as 3.2, and then divided by the square root of the sample size, or square root of 120. That calculates out to 0.292. Step 3 is our rejection rule. We will reject H sub 0 if our test statistic is less than negative 1.96 or our test statistic is greater than 1.96. In other words, we are far enough to the left to show that the average is actually less than 8, or we're far enough to the right to show that the average is greater than 8. And then to calculate our test statistic, we had an 8.5 average from the sample, and standard deviation or standard error divided into that difference gives us a 1.71. Step 5 is do not reject. Um, 1.71 is not less than negative 1.96, nor is it greater than 1.96. So I will say since negative 1.96 is less than 1.71 less than 1.96. So do not reject does not mean that we have proven the null true. It just means that we don't have strong enough evidence to show it's false. See, we turn next to running the same test using a p-value. Again, we will set up the null and alternative hypothesis in the same way. And rejection rule is we'll reject H sub 0 if the p-value is greater than 0.05. Now, to calculate the p-value for a two-tailed test, I'm going to have to calculate a probability and double it. We split alpha originally and are using 0.025 on the upper and lower ends for our decision lines. So when we calculate the area that we usually calculate to get a p-value, we'll have to double it so we can compare it again to the 0.05. First thing I want to do there is to look at the 8.5, and its test statistic is 1.71. So 8.5 is about right there in the distribution. So what we need to do is to find the probability of getting anything less likely than the 8 0.5. Now to do that, I'm going to have to go to the table and look up 1.71. And when I do, notice that the table again always reads to the left. So when I go and look that 1.71 up, I get a 0.9564. But the area that I want is the upper end of that, so I'm going to have to subtract that 0.9564 from 1. And in this case I get 0.0436, which is greater than the 0.025 and supports that the 8.5 sample average is closer to the 8 than that decision line, and that's why we didn't get the rejection when we ran the 5-step procedure. So they are consistent there. But the actual p-value then is going to be taking that 0.0436 and multiplying it by 2 to get 0.0872. So do not reject. H sub 0, since 0.0872 is greater than 0.05. So the risk level is actually higher than what we were willing to allow, and therefore we won't reject H sub 0. Again, just because we're not rejecting H sub 0 doesn't mean it's proven true. There actually, in reality, may be more evidence that it's false, but we're not willing to take the risk to reject it at this point. So the test is basically inconclusive. We have not proven the null wrong, and we have not proven it true. So inconclusive.